Welcome to ECO 442, Operations Research. Study Session 1, Nature and Scope of Operations Research, OR. Introduction. This course will introduce you to the relevant quantitative methods for management decision-making in the modern-day complex business environment. In order to make decisions that will enable managers to perform managerial functions of planning, organizing, directing, and controlling, managers need scientific approach. In this introductory lecture, we examine the nature and scope of operations research. Objective. At the end of this lecture, you shall be able to define and characterize operations research. You shall also be able to explain the scope of its operations and the process involved in its methodology. Content. A. Definition of operations research. Before attempting a formal definition of operations research, we want you to know that there are many terms that can be used to describe the terminology. They include quantitative techniques, management mathematics, analytical techniques, quantitative analysis, business mathematics, and management science. Operations research can be described as the scientific method of providing executive departments with a quantitative basis for decisions regarding the operations under their control. The application of scientific methods, tools, and techniques to problems involving the operations of systems so as to provide those in control of the operations with optimum solution to the problems. The applied decision theory that uses any scientific, mathematical, or logical means to attempt to cope with the executive decision problem. B. History of operations research. Some experts consider the start of operational research to be in the 3rd century BC, during the Second Punic War, when a system of mirrors was used to fire the enemy boats by focusing them with the sun's rays. In 1503, Leonardo da Vinci took part in the war against Prusia and used operations research techniques to construct warlike machines. F.W. Lanchester developed Lanchester Square Law to determine the outcome of a military battle. Thomas Edison made use of operational research during the anti-submarine war. In the 7th and 8th centuries, there were significant contributions to operational research from mathematicians like Newton, Leibniz, Bernoulli, and Lagrange. The origin of linear programming, the most popular techniques of operations research, is generally credited to George B. Dantzig. Dantzig's work was primarily in the search for mathematical techniques to solve military logistics problems when it was employed by the US Air Force during World War II. His research was encouraged by other scholars such as J. von Neumann, L. Ulrich, and T. C. Koopmans, who were working on the same general subject. The original name given to the technique was programming of interdependent activities in linear structure, later shortened to linear programming. After the war, many scholars joined Danzig in the further development of the concept of linear programming. Danzig collaborated with Marshall Wood, Alex Auden, and their associates in developing the simplex method while working on research projects for the US Air Force. Early applications of linear programming were predominantly to military problems such as logistics, transportation problems, and procurement problems. In addition, Worsley-Leotiv's input-output analysis provided a base for the application of linear programming to inter-industry economic analysis. During the 50s and 60s decade, grows the interest and developing of operational research due to its application in the space of commerce and the industry. Take, for example, the problem of the calculation of the optimal transporting plan of sand of construction to the works of edification of the city of Moscow, which had 10 origins points and 230 destinations. The solution involved the use of computer that took 10 days in the month of June of 1958, and such solution contributed a reduction of the 11% of the expenses in relation to original cost. By the mid-1960s, there were large bodies of theory such as linear and dynamic programming, queuing theory, game theory, network analysis, replacement and inventory theories, scheduling, simulation, and so on. An accumulation of successful applications in many arenas: military operations, manufacturing, transportation, communications, construction, healthcare, banking, and many others, and graduate programs leading to advanced degrees in operations research at many universities. C. Characteristics of operations research. The above description of operations research reveals its essential characteristics to include the following. It is system or executive-oriented. Any solution to the problem of a department or part of the organization should contribute to solving problem of the organization as a whole. It uses interdisciplinary teams. The operations research methods are derived from the work of experts from different fields, including mathematicians, statisticians, physicists, psychologists, economists, and engineers. It uses scientific methods. The scientific method of solving problems involves construction of models that represent the systems and its operations. It uncovers connected problems. Solution to a problem involves analysis that reveals all connected problems and attempt to solve all problems together. The approach is not a one-shot problem solution only. It improves the quality of decisions. Though the use of operations research may not lead to best solution, It must at least provide improved solution. For example, you can derive at least bad answer to a problem that you would have given worse answer to without the use of operations research methods. Think over this again. D. Stages in operations research methods. Like any scientific study, operations research study is also a steps as described below. Stage 1. Formulation of problem. This involves clear identification and definition of the problem. You will agree that if the problem is not properly defined, the solution would not be useful. It is important to know that the problem may either be standard or special. Standard problems are routine day-to-day decision-making problems, while special problems are non-recurrent in nature. The formulation of problems should involve analysis of the business environment, the decision maker, the objectives, and the alternative courses of actions. The business environment includes physical, social, and economic factors which may affect the problem under consideration. Stage 2. Model building. This involves a systematic and simplified representation of the real problems. The specification of the model should include all its features and assumptions. It is usually a mathematical model that consists of a set of equations that describe the system and the problem. The equations will include the effective function, also called objective function, and the constraints. The model will include both controllable variables, also called decision variables, and uncontrollable variables. Characteristics of a good model. The number of assumptions should be as few as possible. The number of relevant variables should be as few as possible. Parsimonious. It should be able to adjust to changes in business environment. Advantages of a model. It provides a logical and systematic approach to the problem. It indicates the scope as well as limitations of a problem. It helps in finding avenues for new research and improvement in a system. It makes the overall structure of the problem more comprehensible and helps in dealing with the problem in its entirety. Stage 3. Data connection. Though the previous two stages may also involve collection of data, there is need to collect much more data to be able to solve the model. Useful data include that of cost, revenues, production, stock, etc. Sometimes there is need to quantify factors like risk and uncertainty. Data may be obtained from well-kept records, from current tests and experiments, or even from experience. This is an important stage. For example, imagine a medium-sized linear programming model with 50 decision variables and 25 constraints. We have over 1,300 data elements. Stage 4. Solution of model. This involves determination of a specific set of decision variables that would yield a desired level of output. The solutions obtained could be classified as being feasible or infeasible, optimal or non-optimal, and unique or multiple. A solution is feasible if it satisfies all the constraints, and the best feasible solution is referred to as the optimal solution. If only one optimal solution exists, it is called a unique solution. You may obtain the solution by simulation or by mathematical analysis. Sometimes, you may need to combine both simulation and mathematical analysis depending on the nature and complexity of the problem. The mathematical analysis can either be analytic or numerical. Analytic procedure involves the use of mathematical methods like calculus or matrix algebra. Numerical procedure consists of trying various values of controllable variables in the model, comparing the results obtained, and selecting the values that gives the best solution. The application of numerical procedure ranges from simple trial and error to complex iteration. Stage 5. Interpretation of solution. It is through the interpretation that you will relate the solution to the problems and make meaning out of the solution. You should approach the interpretation with caution because there are problems that reduce the accuracy of the solution. Two of such problems are the accuracy of the data used and appropriateness of the model used. There may also be need to validate the solution with actual data from past records. Stage 6. Implementation of final solution. This involves incorporation of the solution in the operations of the organization. To do this, managers will consider many factors, including, for example, likely disruption to operations, employees, customers, suppliers, and the general public. Stage 7. Review and maintenance. This involves monitoring the performance of the model to determine when it becomes necessary to make adjustments to the model, and finally, when new models should be developed. This is necessary because life is not static, and a solution which is optimum today may not be optimum tomorrow. The solution will remain optimum only as long as the uncontrollable variables remain the same in both terms of values and relationship between variables. E. Scope of operations research. Operations research is useful whenever there is problem of optimization. In defense sector, there is need to coordinate activities, operations, intelligence, administration, training of all defense agencies, Navy, Army, Air Force. In agricultural sector, operations research methods can be used to obtain optimum allocation of land to various crops under the constraints of climate, competing land use, population explosion, shortage of food. In transport sector, operations research methods can be used to regulate arrival time, departure time, waiting time, congestion. Some areas